Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics. Today we are going to discuss about the module Algebraic, Differential and Integral Equations from the paper Mathematical Physics. So students, let us see what we are going to learn in this module. In this module, we are going to learn about the structure of algebraic equation and differential and integral equations. We will discuss their importance and usefulness in physics. Now, algebraic equations, differential equations and integral equations look like this. Let us start with the algebraic equation. A quadratic equation like 3x squared plus 5x plus 7 is equal to 0, you are all very familiar with, or an equation which looks like 5x squared plus 7 divided by 9x to the power 5 plus 11 is equal to 26 are some examples of algebraic equations. In general, an equation is called algebraic if it involves a finite combination of numbers and variables and the algebraic operation of addition, subtraction, multiplication and division. The above equations which we have seen, they involve a single variable x and numbers. More generally, an algebraic equation may have more than one variable. For example, equation like y squared plus 3y plus 5 is equal to x plus 6 plus x squared plus 9, you can see have two variables x and y, and it's a relationship between these two variables. A solution of an algebraic equation involves obtaining the value of the variable for the equation involving a single variable. So if we have a single variable, the solution involves finding out the value of that variable which will satisfy the equation. If we have more than one variable, then we express one variable in terms of other variables called the multivariate equation. In simple cases, it may be possible to obtain the explicit solution, like for example of the quadratic equation which you have learned in your school, that x is equal to minus b plus minus b square by 4c. So the equation which we have shown has a solution x is equal to minus 5 plus minus under root minus 59 divided by 6. Now, a general algebraic equation in one variable can be expressed as f of x as a polynomial in x of power n with the coefficient a1, a2, an etc. written as f of x is equal to x to the power n plus a1 x to the power n minus 1 plus a2 multiplied by x to the power n minus 2, so on and so forth, up to an minus 1 multiplied by x plus an is equal to 0. This is a rational polynomial algebraic equation of degree n, because the coefficient a's are all considered in this equation as rational numbers. A value of x for which f of x is equal to 0 is called the root of the equation, fx is equal to 0. The roots in general can be real or imaginary, and if you have an algebraic equation in one variable of degree n, then it has exactly n roots. That is, a rational polynomial equation of degree n has exactly n roots. Polynomial equations of degree 1, 2, 3 and 4 with coefficient as rational numbers can be solved analytically. The equations of higher order in general cannot be solved analytically. Further, if the coefficients are all integer, then the equation is called Differential equation. Having introduced the algebraic equation in one variable and mentioning the fact that only some equations can be solved analytically, namely polynomial equations of degree 1, 2, 3, and 4. I will now discuss a cubic equation. A general cubic equation is given by x cubed plus a1x square plus a2x plus a0 is equal to 0. This equation, by redefinition of x, can always be reduced to the form x cubed plus qx plus r is equal to 0. Coefficients q and r related to the original coefficients a1, a2, and a0. The roots of this cubic equation are 3 and are given by x1 is equal to y plus z, x2 is equal to y omega plus z omega square, x3 is equal to y omega square plus z omega, where 1 omega and omega square are the cube roots of unity. That is, omega is equal to exponential I times 2 pi by 3, and y and z are given by y cube is equal to minus r by 2 plus under root of r square by 4 plus q square by 27, and z cube is given by minus r by 2 minus under root of r square by 4 plus q square by 27. We will now introduce differential equations. See, the algebraic equation involves the unknown function variable x and its powers. A differential equation involves, in addition to algebraic operations, derivatives of one variable with respect to the other variables. So when you have an equation which relates the unknown function with the derivative of this function, then the equation is called a differential equation. Thus, an equation involving two variables, y and x, where y is unknown and x is variable, of the type dy by dx plus y plus x is equal to 0, then this equation, which has to be solved for y, involves now a relationship between y and its derivatives with respect to x and any function of x, then it's called a differential equation. In the above equation, note that the derivative involved is first order derivative, but in general, derivatives of any order can enter the equation. For example, an equation of the type dy by dx multiplied by the second derivative d2y by dx square plus the fourth derivative dy by dx to the power 4 plus the function y is equal to x square is also a differential equation. Now, as with the case of algebraic equation, it is not always possible to solve the equation and obtain one of the variable in terms of the other, except in some simple cases. Equation given above involve only two variables, y and x, and such equations are called ordinary differential equations. We consider the algebraic equation in one variable. We can in general have the algebraic equation in n variables. An algebraic equation in n variables is a polynomial equation of the form a function of x1, x2, xn, n variables, in general can be written as sum over n1, n2, n3 of the coefficient c, which itself is a function of n1, n2, nn, multiplied by x1 to the power n1, x to the power n2, up to xn to the power nn. So this is the equation which involves the variables x1, x2, xn of all powers related to some function of these variables. Some familiar equations which involve more than one variable, for example, equation which involves two variables, algebraic equation involving two variables x and y, is the most familiar one, is the equation of a circle, namely x square plus y square is equal to a square. Equation involving three variables is the well-known equation of a sphere, which is x square plus y square plus z square is equal to a square. Another interesting equation is called the Cayley's-Sextet equation, and this equation is again equation in algebraic equation in two variables with the reading as 4 times x square plus y square minus x to the power 3 minus 27 x square plus y square whole square is equal to 0. We have defined ordinary differential equations. We also have partial differential equations. So what happens then, more generally, a differential equation may involve more than two variables. Say in the case of ordinary differential equations, there are two variables y and x, and any arbitrary relationship between the derivatives of y and x constituted an ordinary differential equation. A partial equation involves partial derivatives of one variable with respect to the other variables. If that happens, such equations are called the partial differential equations. For example, partial derivative of y with respect to x square, second derivative d2y by dx square plus the second partial derivative of y with respect to z square is equal to y square plus x square plus z square is an example of a partial differential equation. Now remember that partial differential equations of the second kind are one of the most important equations you encounter in physics. You are familiar with solving of boundary value problems in electrostatics. And remember that involves solving of the Laplace equation, which is a second order partial differential equation. And it looks like d2f by dx square plus d2f by dy square plus d2f by dz square is equal to 0, where the derivatives are all partial derivatives. Another familiar examples of second order partial differential equation is the celebrated heat equation, which is given by d2f by dx square plus d2f by dy square plus d2f by dz square is equal to 1 by c df by dt. As usual, the derivatives are partial derivatives of f with respect to x, y, z and t respectively. Then undoubtedly you are familiar with the wave equation. In fact, when you solve the Maxwell equation in electrodynamics in free space, in the absence of any charges and currents, you get the familiar wave equation satisfied by the electric and magnetic fields. The wave equation in 3 dimensions looks like d2f by dx square plus d2f by dy square plus d2f by dz square is equal to 1 upon c square d2f by dt square, where f in the case of electrodynamics, for example, is the electric field or the magnetic field which propagates with the velocity here, which is c. Another very important and familiar partial differential equation is the Schrodinger equation, which occurs all the time in problems involving non-relativistic quantum mechanics. The Schrodinger equation looks like minus h cross square by 2m d2 psi by dx square plus d2 psi by dy square plus d2 psi by dz square plus v, which is a function of xyz into psi, is equal to minus ih cross d psi by dt, where psi is the famous Schrodinger wave function. A general differential equation of order n involves the nth derivative of the function y with respect to s. So it looks like a function of x, y and the derivatives of y like dy by dx, dy square by dx square up to dny by dx square. A relationship between the derivatives of the function y with the variable x equal to 0 is a general differential equation of order n. The order of the equation is the highest derivative which exists. The differential equation is said to be linear if there is no term in the equation containing the product of y and its derivatives. That is, either y or any of its derivative occur linearly in the equation. Only then the equation is said to be linear. The equation is homogeneous if there is no term independent of y or its derivatives. So I will now give some examples where the differential and integral equations occur in physical problems. So given a physical problem, we first set up the corresponding equation and then solve it. So we'll see how these equations are set up. So I will start with an example for mechanics, which is a very simple example. A particle of mass m is moving in the x direction, so it's a one-dimensional motion, and is acted upon by a force equal to minus kx, where k is positive constant and x is the coordinate of the particle. We will set up the equation of motion of this particle and solve it given the initial conditions that at time t is equal to 0, the particle was at x equal to 0 and its velocity was equal to v. You must have immediately recognized that this is a problem of one-dimensional harmonic oscillator. How to set up the equation? So we use Newton's second law, which says that mass into acceleration is equal to force, and acceleration in the in a one-dimensional motion is d2x by dt square. Therefore, the equation which we immediately get is m times d2x by dt square is equal to minus kx, where m is the mass and k is the force constant. So this is a second order ordinary differential equation. Its general solution is very easy to obtain, as you can verify. That solution is x is equal to a sine omega t plus b cosine omega t, where omega is under root k by m and a and b are constants. The constant a and b are to be evaluated from the initial conditions. So using the initial boundary conditions, that at t is equal to 0, x is equal to 0, and dx by dt is equal to v. Substituting this in the solution, we immediately get b is equal to 0 and a is equal to v by omega, and this completes the solution. Now let us see how does the integral equation look like. Integral equations involve, unlike differential equations, the integral of a variable, not the differential. So they involve, like the differential equations, at least two variables, and the relationship between them involves an integral over one of them rather than a differential, as in the case of differential equations. Thus, an example of an integral equation is e to the power x is equal to the integral from a to b of some function k of variables x and I, y s integrated over ds, where kxs is called the kernel and y is the unknown function. In this, a and b are constants, and k as a function of two variables x and s is given function, and it involves variables y and x, and the equation is a relationship between them involving algebraic operations and integration. Now, what is the use of integral equations? The integral equations crop up naturally in a variety of problems in physics and mathematics, just like the differential equations. So I now will formulate the problem in the same way for the case of integral equation. That is, we consider a problem which involves setting up of integral equation. This problem is comparatively more involved than setting up of a differential equations. So let Pt be the rate at which goods have to be replenished. What does it mean? It means that in the time interval t and t plus delta t, the amount of goods bought is Pt into delta t. Now, if S0 is the stock of goods at time t is equal to 0, then at time t, the amount of goods which are not sold out or destroyed is S0 minus S0 into 1 minus lambda t, where lambda at the time t is equal to 0 is equal to 0. Now let us consider that the stock is being replenished and is replenished now in this case during the time interval from 0 to t. The amount of goods which are replenished during the interval tau to tau plus delta tau, where tau lies between 0 and t, is p tau into delta tau, because p tau is the rate at which the goods are replenished. At time t, which is t minus tau times further from tau, the fraction of the remaining stock will be p tau into delta tau into 1 minus lambda, a function of t minus tau. Thus, the total stock of the goods at time t is the amount of goods which remains. Some stock is destroyed and some stock is replenished. Therefore, the total stock of goods at time t is S0 times 1 minus lambda t plus an integral from 0 to t pt 1 minus lambda, a function of t minus tau, d tau. Now, if the stock has to remain unchanged, then this must be equal to S naught. Therefore, S naught is equal to S naught into 1 minus lambda t plus 0 to t p tau 1 minus lambda t minus tau d tau is the equation for the unknown variable p of t. Thus, we'll end up with an integral equation for the unknown variable p of t. Thus, given the original stock S naught and lambda t, a solution of this equation will be the answer to the question which we have posed. So, for the stock to remain unchanged, this must equal to S naught. Therefore, S naught is equal to S naught into 1 minus lambda t plus 0 to t, the integral over d tau, where the integrand is pt into 1 minus lambda t minus tau. And this is the integral equation corresponding to the question which we had posed. A second example, which involves setting up of the integral equation and solving it, occurs in the study of population growth. Let us assume that the births in a given population, and let us only confine ourselves to the female population. So we assume that the births in a given female population take place continuously in time t. Now we consider relating the number of male births per unit in a population Bt. So population is B, which is a function of time t. So at a given time t, B is the population of the female members of the group. Then we consider the relation of Bt to its value at an earlier time. By definition, Bt dt is the number of females born in the time interval between t and t plus dt. Now, out of these population, there will be a survival rate because some of the members will die out, and there will be an increase in population because of the fertility rate, because of the new baby girls will be born. So let us introduce a survival rate S of t for females in this population, where S of t is the fraction that is lying between 0 and 1 of females which surviving at time t after birth, and a fertility rate f of t, which is defined as that ft dt is the number of females born to a female during the interval between t and t plus dt in her lifetime. Now the female population bt at time t will receive contribution from the females which are already present at a given time t is equal to 0. Let us call this g of t. Then females born out of females that were born during the time interval from 0 to t. Consider the females born at time t prime before t, so that their age at time t is t prime. The birth rate of these females is b in a function of t minus t prime. From the definition of the survival rate as t and the fertility rate f of t, the contribution to this population bt from this category during the time interval dt prime at a time t prime prior to t is b a function of t minus t prime into s function of t prime into f a function of t prime, that is the population at t minus t prime multiplied by the survival rate at t prime and multiplied by the fertility rate at t prime. Hence, the population time tbt is equal to g of t plus the integral of s of t prime, f of t prime, b of t minus t prime integrated over t prime from 0 to t. This is the celebrated Lotka integral equation for the unknown function b of t. So, students, let us summarize what we have learned in this module. In this module, we learned that a rational polynomial algebraic equation of degree n given by a function f of x as a polynomial of degree n with the coefficients which are rational number. So f of x is equal to x of x to the power n plus a1 x to the power n minus 1, so on and so forth, plus an is equal to 0. This algebraic equation has exactly n roots. Polynomial degree equations of degree 1, 2, 3 and 4 with coefficients as rational numbers can be solved exactly. If the coefficients are integers, the equation is called Diophantine equation. A general ordinary differential equation of order n is given by a functional relationship between the variables x, y and its derivatives up to degree n, for example, is equal to 0. The differential equation is linear if there is no term in the equation containing the product of y and any of its derivatives, and the equation is said to be homogeneous if it contains no term independent of y and its derivatives. Such equations are known as ordinary differential equation. A partial differential equation has more than one independent variable and it involves partial derivatives. An integral equation, on the other hand, involves at least two variables and the relationship between them involves an integral over one of them. For example, the equation f of x is equal to integral from a to b over ds, where the integrand is k, a function of x and s, and g, another function of s, plus some other known function, capital F of x. Thank you.